This is mathheals.com, where you can find more links to math YouTube videos if you wish. And we're going to take a look at estimating a population mean. Now the first thing we'll do is wait till all the sirens go by my house. Ooh, fire, fire, fire. Okay. Students' t-distribution. It says, suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution of t equals x bar minus mu over s divided by square root of n follows students' t distribution within minus 1 degrees of freedom. Now, assumptions are sample data comes from a simple random sample or randomized experiment. Sample size is small relative to the population size. So little n, our sample size, is less than or equal to 5% of our population size. Capital N is our population size. Data comes from a population that's normally distributed or the sample size is large. If it's greater than 30, it doesn't necessarily have to be normally distributed. Is what that's saying. Well, the first thing we need to take a look at is how to find the critical value. T under, and then T sub alpha divided by 2. So let's look at the steps. It says find the area in one tail. Find your degree of freedom. df is equal to n minus 1. I always like to give a example of a degree of freedom just in my own life. And it's not the same idea as data, but it kind of helps you to think about what is the degree of freedom. My wife and me play this little game where she'll ask me where I want to go eat dinner at. And oftentimes I say I don't care. And she says, no, I want you to tell me, where do you want to go eat? And I say, okay, well, let's go to Old Chicago. No, I don't want to eat there. We go there all the time. Okay, I want to go over to this Chinese restaurant. No, I don't feel like eating that. After 4 or 5 of these, of her shooting down my ideas, then she tells me where we're going. I really don't have any kind of freedom there. She chooses. There's 2 of us. The degree of freedom, if we take 2 minus 1, would be 1. She has the freedom. After she makes the choice, then I have no choice. If you're graphing something in college algebra, you go y is equal to 3x minus 1, and you're building a t-chart, you can put any value in for x. But after you pick a value for your x, and y has no choice. So again, same type of idea. And with data, we have a similar concept. Now then we look up the value in the t-distribution table. So let's look at some examples. It says find t-value such that area in the right tail is 10%. So we got our picture here. And here's our 10% with 12 degrees of freedom. So it tells us df is 12. Well, it's a little bit confusing because on some of these we'll be wanting this value, and some of them we want this value. Now you look it up in the table the same way. So if I find my table, wherever it might be, there it is. Here's our t-distribution table. Personally, I think this picture at the top and this description here is wrong. They say area in the right tail. Well, you really should say area in one tail. Shouldn't say area in the right tail. In some problems we're going to see later on, when we get to claims, we don't have a right tail, which then doesn't make any sense when you're saying what is the area in the right tail. But it's area in one tail. Well, here we got area in one tail is 0.10. So I'm going to come and look in the column dealing with 0.10. We said our degree of freedom is 12. So I come down here. I'm in my 0.10 column. I'm going down to 12, and we get 1.356. Which would be our answer. So that's our t alpha divided by 2. Now, if the value we're trying to find is on the left side, right here, it would still be 1.356, but it'd be negative. So that's the difference between the two. I think we actually got an example of that. Okay, find the t-value such that the area in the right tail is 0.05 with 20 degrees of freedom. Okay, so they're telling us this is 0.05, and df is 20 degrees of freedom. So this is the value we're trying to find right here. And I'm not going through those steps, but the steps we're doing is these right here. Okay, let's go look this up. 0.05 would be this column right here, and what did I say, 20 degrees of freedom. So 0.05, 20 degrees of freedom, we have 1.725. Now since it's on the right side here, it'd be a positive 1.725. And that's your answer. Okay, number 3. It says find the t-value such that the area left of the t-value is 0.01. Left of it. So they're telling you the area of the left is 0.01, so they're really asking for the one here on the left side. And degrees of freedom is 9. So I'm going to go look up, again, in our table, it should say area in one tail. So this is 0.01. So I'm going to look in the 0.01 column. And degree of freedom of 9. So I come down here to 0.01 and 9, and we get 2.821. Now, since it's on the left side, then it's going to be negative. So that'd be our value we're trying to find. And I think we got one more of those. Find the t-value corresponds to 90% confidence. Assume 15 degrees of freedom. And 90% confidence. So we put 90% in the middle. All adds up to 100%. So if we got 90% in the middle, then 10% goes in tails. And since I got 2 tails, I'll put 5% in each tail. And this is assumed value, unless it specifically says find the one on the left side. This is the one they're talking about. So we're going to look up, what was our degree of freedom? 15. And area in one tail, doesn't matter which one you pick, but the area in one tail is 0.05. So I'm looking the 0.05 column, and I'm looking for degree of 15, which I come down here to 0.05 to 15, we get 1.753. Now since it's on the right side, then it'll be positive. And actually, this notation there is not what we're looking for this, but again, we get more into that later on. But anyway, that's our value on the left side. Let me save that. This is estimating the population mean, I'm assuming. Estimating the population mean. ES, estimating a population mean. And page 01.pdf. There we go. Okay, let's take a look at confidence intervals. Okay, so for our confidence interval, our lower bound is x bar, which is sample mean, minus our critical value. Now this is the one on the right side, times s, which is our sample standard deviation, divided by the square root of n. N is our sample size. Then the upper bound is x bar plus t alpha divided by 2 times s divided by square root of n. And x bar is our point estimate. So that's our best guess. That's the middle of our interval. Now, to do this on a TA3, TA4, to find the confidence intervals, you press your Stat button, choose your test menu, choose your T interval, highlight stats or data if given raw data, enter your standard deviation, mean, N, and C level, or whatever is appropriate, highlight calculate, and press enter. And then E, if it's asked for the margin of error, is equal to your upper bound minus x bar. Okay, let's take a look at a problem that kind of explores this a little bit. Tells us our lower bound is 20, our upper bound is 28. It says determine the point estimate of the population mean, and then the margin of error for each confidence interval. Well, to find the point estimate, is x bar, symbol-wise. And to find it, it's in the middle of this interval. So we'll take our lower bound plus our upper bound, and we'll divide by 2. So we got 20 plus 28 divided by 2, which is 48 divided by 2, which is 24. Now when you could actually see, 24 is halfway in between there. Now our margin of error. Here you can take your upper bound minus your point estimate. So upper bound minus x bar. So our margin of error is upper bound, which was 28, minus x bar, which is 24. So our margin of error is 4. And those would be our point estimates and the margin of error. Well, this next problem is asking us to actually find the confidence interval by hand and then by TA3, TA4. So we'll do it in both ways so you see both forms of this. Now, first problem here says a simple random sample of size 25. Let me do this by hand first. It says a simple random sample of size 25. So that tells us N is 25. Has a sample mean of 20.2. Sample mean is x bar. And a sample standard deviation of 2.1. That's S. So S is equal to 2.1. And it says construct a 95% confidence interval. So that's what we want. 95% confidence interval. Okay, to do it by hand, we need x bar. We have x bar. We need S. We have S. We need N. We have N. The only thing we don't have is this weird looking thing here, T alpha divided by 2. So let's take a look at how to find that. So draw our picture. This right here is our T alpha divided by 2. Now it tells us 95% confidence, so we'll put 95% in the middle. All this adds up to 100%, so if 95% is in the middle, then 5% is in the tails. And since we have two tails, we'll split it up into our tails, so we'll put 0.025 in each tail. Now we also need our degree of freedom. Degree of freedom is n minus 1. So we'll have 25 minus 1 gives us 24. So our critical value, we look up in our table in the back. Okay, so area in one tail, 0.025, wherever that be. It'd be right here. Now again, it doesn't matter which tail you pick, it's just area in one tail. And our degree of freedom we said was 24. So 0.025, go down 24. That tells us 2.064. And that's our critical value. Now for our formulas. Our lower bound is equal to x bar minus t alpha divided by 2 times s over square root of n. Well, x bar is 20.2 minus our critical value, so we got 2.064 times s, which was 2.1, divided by the square root of n, and which is 25. So our lower bound, let's see what that gives us. 20.2 minus 2.064 times 2.1 divided by the second x squared for the square root of 25. Enter. And I don't know, I'll take it to 2 decimal places, I guess. 19.33. There'll be our lower bound. Now for our upper bound, we're going to have x bar plus our critical value times s over square root of n. So this is going to be 20.2 plus 2.064 times 2.1 divided by square root of 25. Nice part about the calculator is if you've already typed in that previous one, if you do second enter, it'll bring up the previous entry, and you can up arrow and then right arrow and just change that to a plus. And then enter. And we get 21.07 for upper bound. So our confidence interval will be 19.33 and 21.07. And that's our answer. Well, let's do it on the calculator now. So number 6, calculator. Specifically at T83 or 84 series. Okay. There it is. Scroll down a little bit more. It says a simple random sample of size 25, so n is 25. Has a sample mean of 20.2, so x bar is 20.2. And a sample standard deviation of 2.1, so s is 2.1. Construct a 95% confidence interval. Our steps just basically tell us go do a t interval. It's nothing exciting there. I'm going to press my stat button, and then I want to right arrow over to tests, and I want down arrow to t interval. I think that's number 8. This one right here. And then press enter. Now, up here where it says input, we either want data or stats. Data is when you're given raw data. Stats is when you're given summary statistics. Summary statistics is what we got right here. So we want to right arrow over and put our flashing cursor on stats, and then press enter. And you should see your parameters change. So it should say t interval at the top, and you should say stats. Now if I down arrow, it's asking us for x bar. Well, that was 20.2. Enter. It's asking us for SX. That's the calculator's version of S, so that's 2.1. Enter. Then it's asking us for N, which we said was 25. then enter. Then it's asking us for sea level. Sea level is our confidence interval it's asking for. It's asking for 95%. So I'm going to put in 0.95. I already had 0.95, but you might not. So I put in 0.95 and press enter. And it goes down to calculate, and then you press enter one more time. And it gives us 2 decimal places. We got 19.33 and 21.07. And that's our answer. Now it also, if it was given raw data, see how it gives us X bar? So it gives us the point estimate right below it. Let me save that and we'll look at our next problem. Number 7. Okay. Number 7 by hand first. It says, say, age of a student at the college follow a normal distribution. If a sample of 15, so n is 15, has an average age of 18.2. So X bar is 18.2. It says average, which is mean, and it's referring to the sample. So that means it has to be sample mean, with a standard deviation of 0.5. So S is going to be 0.5. Again, it's still referring to the sample of 15, so that's why it's S. Construct a 99% confidence interval for the population mean. So 99% confidence interval. That's what we want. Come back up here to our formula. Look what we need. We need X bar. We have X bar. We need S. We have S. We need N. We have N. The one thing we don't have is this critical value here, this T alpha divided by 2. So we want to find T alpha divided by 2. Now we want to draw our picture. We want a 99% confidence interval, which means we put 99% in the middle. Now, if 99% is in the middle, then 1% is in the tails. And you divide that by 2, and we would have 0.005. Again, it all has to add up to 100% or 1. Now, the T critical value we're looking for is right here. We need our degree of freedom. Degree of freedom is n minus 1. N was 15, so we got 15 minus 1, or 14. Now we're going to go look it up in our table. So area in one tail is 0.005. Area in one tail is 0.005. And then degree of freedom is 14. So 0.005 and 14. And we get, assuming my eyes aren't getting off, 2.977. 14, 2.977. Let me make that a little bit bigger. Might be a little easier for you to see. Okay, 0.005 and 14. So 0.005 and 14, we get 2.977. Okay, well now we have everything we need, so let's go plug it in our formula. Lower bound is equal to X bar minus our critical value times S divided by the square root of N. Right there. Okay, X bar is 18.2 minus 2.977 times S, which was 0.5, divided by square root of N, so square root of 15. Let me scratch my head here for a minute. There we go. So we got 18.2 minus 2.977 times 0.5 divided by second x squared for the square root of 15. And let me double check on my numbers. Okay, so then our answer will be 17.82 for the lower bound. Well, now we need upper bound. Upper bound is x bar plus our critical value times s divided by square root of n. X bar was 18.2 plus 2.977 times 0.5 divided by a square root of 15. That's already in my calculator from the previous entry, so if I do second enter, that'll bring up the previous one, and I just come up here and change the minus to a plus. Or type it all in again if you're not very good at technology. And we get 18.58. So our confidence interval will be 17.82, comma 18.58. And that's our answer. Let's redo this using the calculator. Okay. It says ages of students at the college follow normal distribution if a sample of 15 students, so n is 15, has an average age of 18.2, so 18.2 with standard deviation of 0.5, so s is equal to 0.5. And we want a 99% confidence interval. Let me grab a drink here real quick. Just a sip. And so now we'll go to our calculator. I'm going to press stat, right arrow to test, down arrow to t-interval. I think it's number 8 again. Boy, my eyes are bad. There it is, t-interval. Okay, now data is when you're given raw data, and then the stats is when you're given summary statistics. And again, we got summary statistics, so we're going to go with that. X bar was 18.2. Sorry, I was a little distracted by something going on in my house. S is 0.5. I'm back now. Okay, N is 15. Sea level is 0.99. Enter, and then enter and calculate. And our answer to 2 decimal places, 17.82 and 18.58. Now you will find a slight differences in some of these, but the calculator will actually be more precise. So if you're wondering, the book is limited by tables, so sometimes you have to go with whatever's closest. You know, if it's asking you for a 97% confidence interval, and you look in your table, and you can't find a value that corresponds to area in one tail, well, you go to whichever one's closest, and you kind of use it as your basis, if you're using tables. Let me save that, and we'll look at the next problem. And let me try to find my calculator here somewhere. Actually, I guess I can just use the one on here. Okay, let's look at number 8 by hand. Okay, sample scores are listed below. Assume the scores are normally distributed. Construct a 90% interval for the population mean. So we want a 90% interval, confidence interval, that is. Okay, so we got some numbers. Now for our formula. I'll come back to those numbers here in a second, but let's look at just where we're headed. Of course, this value we can find very easy, but x bar s, we're not given x bar and s. We have to find it. So I'm going to go ahead and put my values in a column. So I got 80, 82, 82, 84, 90, 95, 97, and 97. 80, 282s, 84, 90, 95, 97, 97. Okay. Actually, I lie. I'm going to use my calculator. Where's it at? There it is. Okay, now that I got those written down, I'll go back to my formula. We need x bar. Well, we know how to get that. We're going to take this. We're going to add them together. So I got 80 plus 82 plus 82 plus 84 plus 90 plus 95 plus 97 plus 97. So 97, 97, 95, 90, 84, 82, 82. Okay, so that gives me 707. X bar is going to equal to that sum divide by how many we have. 1, 2, 3, 4, 5, 6, 7, 8. So divide by 8. So we got 707 divided by 8. And I get 88.375. Well, now we want to come up with another column, x minus x bar. So we'll take 80 minus, 82 minus, 82 minus, 84 minus, 90 minus, 95 minus, 97 minus, 97 minus, and our mean is 88.375. So I'll go ahead and put that in everywhere. Okay. So I'm just going to type all these in my calculator so I don't screw any of them up. I don't want to make a basic math error and have an error sitting on my video. I get enough of those errors. Negative 8.375. I'll do a second enter, bring up my previous entry. And then negative 6.375, and this one will be negative 6.375. And then this will be negative 4.375. And then 1.625. $6.625. And 8.625. And this is 8.625. Okay, so now I need x minus x bar squared. So I'm going to take this value I just found and I'll square it. So I got negative 8.375 squared. Negative 6.375 squared. Negative 6.375 squared. Negative 4.375 squared. 1.625 squared. 6.625 squared. 8.625 squared. And 8.625. Why would anybody do this by hand if they could use a calculator? I don't know. 8.375. It's like, and who really wants you to in real life? 70.140625. Worst thing you can do is round too early in a problem. 6.375 squared. 40.640625. And this is 40.640625. 4.375 squared. 4.375 squared, and we get 19.140625. 1.625 squared. 2.640625. 6.625 squared. 43.890625. I would use a shortcut formula for doing this if I was going to do a lot of these by hand. I don't plan to do a lot of them by hand, so I'm just using our basic one here. 74.390625 and 74.390625. Okay, and we want to add all those together. 70.140625 plus 40. It'll be a miracle if I don't screw this up. 640625. 40.640625 plus 40.640625 plus, kind of double check myself as I go along here, 19.140625 2.640625 43.890625 plus 74.390625 plus 74.390625. Assuming I typed it all in correctly, which is doubtful, but let's see, 365.875. Okay, now time to find our S. S, this is the sum of x minus x bar squared. S is equal to the square root of the sum of x minus x bar squared divided by n minus 1. So we got square root of 365.875 over n minus 1. I think we had, how many numbers did we have? 8, was it? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so 8 minus 1. And I don't want to round this at all. So 365.875 divided by 7. 7.229651246. Now I'm gonna actually do this, cheat a little bit here. I'm gonna look at my calculator and find the standard deviation and see if I got at least that part right. Because if I got an error, I'm gonna go ahead and correct it before I go on. we're going to get to the by hand. You'll say, man, this is so easy by calculator, and you'll think, man, why did he ever even show that? Some people don't have a calculator, and they like to do things by hand. Oh, that's a miracle. I actually got it right. Okay, and X bars. Okay. Okay, now we found X bar and S. And we said N was 8. So I'm going to go ahead and jot that down. Back to our formula. We got X bar, we got S, we got N. We need the T value now. Okay. So when you're given raw data and you're doing it by hand, first thing you got to do is you got to find X bar and S and N. Now the second thing we're going to do is we're going to find our critical value. What was this one? This was 90% interval. So put 90% in the middle. Was 90%, right? Yeah, 90%. Means we split up 10% in our tails. So I'll put 0.05 here and 0.05 here. And again, this is our critical value. We need degrees of freedom, which is n minus 1. So we got 8 minus 1, or we got, that's nice, 7. Not sure why that went to a green screen there. So let's look this up in our table. Area in one tail is 0.05. Right here. Degree of freedom is 7. So 0.05 and 7, I get 1.895. Let me double check that. Throws me off when my screen just all of a sudden goes green like that. Yep, that's right. Okay, now we're ready for our formulas. So our lower bound. That's going to be X bar minus our critical value times S divided by the square root of N. X bar. What was X bar? X bar was 88.375. So 88.375 minus our critical value, which we just said was 1.895, times S, which is 7.229651246, divided by the square root of N, and N was 8. So lower bound is going to equal something. Let me go. I shall type that in here so you see it. Okay. So we've got 88.375 minus 1.895 times 7.22965 1246 7.22965 divided by square root of 8. So divide by second x squared and then 8. Enter. So assuming I didn't make a basic math error somewhere, it's 83.53. For our upper bound, that's X bar plus our critical value times S divided by the square root of N. So we got 88.375 plus 1.895 times 7.22965 1246 divided by the square root of 8. Only thing changes is that sign right there. So let's go here and I'll do second enter to bring up the previous entry. And I'm going to go up here and change that minus to a plus. And we got 93.22. So our answer is 83.53, comma 93.22. Now let me jot that down somewhere. How can I not have any paper in my room here? That's a rhetorical question. Let's see. 83.53, 93.22. Be a miracle if I get to if I didn't screw up somewhere in that calculation. Okay, so let me save this, and then let's look at it on the calculator. Okay, number 8 revisited. Number 8 on the calculator. Okay, want a 90% confidence interval. And we got 80, 82, 82, 84, 90, 95, 97, and 97. Okay, on the calculator, if you're given raw data like that, you want to go put it into L1 first. So we'll press Stat, press Enter on Edit. If you already have numbers there, press Delete until they're gone. Don't delete your L1 though. And then we'll put in 80, Enter, 82, Enter, 82, Enter, 84, Enter, 90, Enter, 95, Enter, 97, Enter, and 97, Enter. I'll go double check my numbers. Okay. Now after you do that, exit out. So do second mode. Now we're going to go to our Stat again and go over to Tests. So right arrow over to Tests, and we'll go down to Z interval again, or T interval, sorry. Press Enter on it. Now we're given raw data. So instead of wanting stats, we want to put our flashing cursor on data and press Enter one time. And you should see a change to the following parameters. Now I'm going to down arrow to list, and I want this to be L1. If it isn't already L1, do second and then 1 to put L1 there. Now here our frequency should be 1. If that doesn't say 1, press your alpha key one time, and then press your number 1. And now our C level. We said 90%, so put in 0.90 and calculate. And I don't have to curse because it looks like the same. So 2 decimal places, 83.53, at least that part is, 93.22. And that's our answer. Now sometimes on these problems they'll ask you to find a point estimate too. So if they're asking you to find a point estimate, well, first go through and just find your interval on your calculator. You know, in your data, do what we just did. It'll give you the point estimate. See how it gives you that? So our point estimate is 88.375. Anyway, that's how you do it on the calculator. That was interesting. I hadn't done one of those by hand for I don't know how long. Probably when I was 21. Well, let's take a look at how to calculate to find a sample size. So we want to know how many should we sample. And this is our formula. This sample size to estimate population mean. We got N is equal to, and then this is a Z score. So this is Z sub alpha divided by 2 times S over E squared. Now different books will have different variations of this. This book went to something kind of different, which is this formula. Some books, instead of having S there, will put sigma, population standard deviation. I never really got to read in the book why he chose to do what he did here, but he went away from that. And I think the idea is that most of the time you don't know what the population standard deviation is, and that's why an S, like a previous sample standard deviation, is a best guess. Well, if you don't have S, you don't have a previous sample standard deviation, then use sigma if you're given that. So again, that's the very little difference in the formula. Now E is your desired margin of error. And then of course Z alpha divided by 2. I said this critical Z-score based on desired degree of confidence. Let's take a look at some sample size problems. If we wish to estimate the mean age of students at the college with 95% confidence. So we want 95% confidence within 0.2 years. Well, within is always your E. So E is 0.2. How many students? Now notice the difference in this. It's not asking about confidence interval anymore. It's asking how many should we sample, assuming the sample standard deviation from last year was 1.3. So S is 1.3. Okay, let's go up to our formula. The things we need are these three right here. Well, S we're given, E we're given. What we don't have is this Z, this critical Z-score. So let's find that. Draw our picture. 95% confidence. We put 95% in the middle. Now all of this adds up to 100%. So if we put 95% in the middle, we're going to split the 5% into the tails. So this will be 0.025, and this will be 0.025. Now our critical Z-score is right here. And I'll show how to find it using the tables in the back. And also show via the calculator. Now the tables in the back are based upon the area to the left. So the area to the left is 0.025 and 0.95, so that'd be 0.975. So if I come back to my table, I'm looking for my normal distribution here. There we go. And we're going to look for 0.975 in our table. Here's 0.975 right here. If I go over to the left, that tells me it's 1.9. If I go up, that tells me it's 0.06. So that would be Z is equal to 1.96. Again, we're looking up the area to the left of this value. So we have to add up both this and this, which gives us a 0.975. I'm looking in the middle here, and I'm looking for the value that's closest to 0.975, and here it's exact. So I come over here, 1.9 and 0.06. This is our hundredths place. So that's where we get to 1.96. Now to do it on the calculator, we're going to use INV norm, and it's always the area to the left. So again, we add these together, and we're going to put in 0.975. And if I come here, do second vars, choose 0.975 for our INV norm, and we get 1.96 if I take it 2 decimal places. Okay, it doesn't matter whether you do it via tables or TI3, TI4. This next part you have to do by hand anyway. There is no calculator function for it. So our formula says N is equal to our critical Z-score times S divided by E squared. Well, the Z-score was 1.96 times S. S was 1.3 divided by E, which is 0.2, and squared. And you always round up. That ensures, no matter what your decimal is, you always go up to the next whole number. That ensures that you got enough in your sample. Okay, so I'm going to put in beginning parentheses 1.96 times 1.3 divided by E, which was 0.2, close parentheses, and then this x squared, and then enter. And our answer is 163. Again, you always go up. Always round up. Okay, let's look at our last problem. Sample size. If we wish to estimate the average hours that students watch television at 99% confidence, within 1 hour, so they're telling us E is 1. How many students should we sample, assuming the sample standard deviation from last year is 2.1? So S is 2.1. Okay, well, let's draw this. 99% confidence, we put 0.99 in the middle. We got 1%, we're going to split into our tails. So this will be 0.005, and this will be 0.005. And this is our z-score. And if we're using tables, or if we're using tables or the calculator, you actually have to do area of the left. So we're going to add this plus this. So we got 0.995. So let's go look it up in our table. 0.995. 0.995. Looks like it's halfway in between 0.9949 and 0.9951. So halfway in between. Let's go over here. This is 2.5. And, of course, my eyes just got off there. Okay. Here's this and this. Halfway in between this. I come up to here. It's 0.07 and 0.08. So we're going to have 7.5, like that. That's the worst part about doing it via the calculator and then comparing it to your results by hand. Sometimes in the tables you use 2 decimal places, sometimes you use 3 if it's exactly in between 2 values. Well, let's do this on the calculator. So I'll do second vars, choose INV norm, and we're going to pass in the area of the left, which area of the left of this, again, is 0.995. So 0.995 and press enter. And I'll take it, that's interesting, 0.995, 2.5, it's not 7.75, is it? It rounds up. 2.576. Now, realize the more decimal places we take it to here, the more accurate our answer will be. But that's interesting. Did I look that up correctly? I would assume the rounding would have been fine on that. Let me go look up on the table again. Now I'm wondering. 0.995, 995, right here. So yeah, it is exactly halfway in between here, isn't it? 2.575, 2.575, yeah. Oh well. Let's plug it into our formula now. So we've got our critical z-score times S divided by E and squared. Which one to use? I'll use a calculator. I like calculator better. I'm more of a calculator person nowadays. 2.576 times S, which is 2.1, divided by E, which is 1, and then squared. Okay, so beginning parentheses, 2.576 times 2.1, close parentheses, I don't need to put the divide by 1, and then squared. And I always round up, so it'll go to 30. And that's our answer. Let me save that. And then I want to talk a little bit about the changes that this particular textbook did and the way it used to be, just so you know. Your textbook, if you're in a different class, may be using the old way of doing this. If we have a confidence interval for a mean, the old technique it used was if sigma was known and it was a large sample, you use z interval. If sigma was not known, then you used t interval. Now, you don't need to worry about that in this book. Of course, it may change, but this current edition is using t interval for 100% of the problems. But again, depending upon which book you have, you may have to do one or the other. Now, if you're wondering where z interval is, let me just introduce it a little bit. If you press stat, go over to tests, you may have noticed it. Number 7 is our z interval. So I'll go down to it. We press enter on it, and let's look what it's looking for. Of course, I don't want data. I'm going to go over to stats, so right arrow over that, press enter. It's asking for many of the same things. Sigma, it's asking for population standard deviation. The other one was asking for S. X bar, well, the other one was asking for X bar 2. N, the other one was asking for N, and then sea level. So it's not hard. Again, it's a lot easier. For our particular textbook, we're just going 100% of t interval. And some books, and it gets this a little bit weird sometimes, some books, when you talk about a large sample, they'll assume that sigma is equal to your sample standard deviation. So if you're given a sample, if you got a large sample, they'll assume that that's sigma. And then some books will use the z interval. If not, to muddy the waters a little bit more. So it gets a little bit confusing. And now that I've muddied the waters, I think we're done with this section. So let me save this. And actually, let me double check. Yeah, that was my last problem. So let me stop the recorders.